In this video, I want to use Fubini's theorem to evaluate a double integral. So I'm being asked to integrate the square root of x over y squared over the rectangular region where x is between 0 and 4 and y is between 1 and 2. Fubini's theorem tells me I get to evaluate this double integral as an iterated integral. So it's up to us in this problem to pick the order of integration. Now usually if someone just told me to integrate, I'd pick an order of integration and go with it. And so I'd look at the problem and say, well, which order seems to be easier? And if I couldn't tell, I might just flip a coin and pick one. Because this is our first example, I'm actually going to do this one twice. I'm going to do this with both orders of integration. So first, I'm going to integrate with respect to x first. I'm also going to rewrite my integrand using powers of x and y. All right, so I'm going to integrate with respect to x first. So the dA is now a dx dy in my iterated integral. And this reminds me that when I defined the double integral, right, this dA came from a delta a that was a delta x times a delta y. So this feels right to me that my differential operator goes from being a dA with respect to area and is now going to be with respect to x and then y. Okay, well, looking at these bounds, in the x direction I go from 0 to 4, and in the y direction I go from 1 to 2, and now I can simply integrate. So my first round of integration treats y like it's a constant, and I integrate with respect to x. All right, so that's x to the 3/2 times 2/3, that constant just hanging out there, and I need to evaluate from x is 0 to x is 4, and I'll still be integrating with respect to y in a moment. And I'm going to sneak my work up here. All right, so plugging in a 4, the square root of 4 is 2, 2 to the 3rd is 8. It's going to give me a 16/3, and when I plug a 0 in, everything vanishes. So just a 16/3 times y to the -2nd dy. All right, add 1 to the exponent, I'll get y to the -1st times that -1. So -16/3 y to the -1st, evaluated from 1 to 2. So let's see, it's going to be -16/3. First times a 1/2. And then a -1. 1/2 minus 1, that's going to be -1/2. I'm going to get a positive 8/3. There's the value of my double integral, but I did say I was going to do this one twice. So now I want to see what happens when I reverse the order of integration. Hopefully I also get this 8/3. Same integrand. Now this time I'll be integrating with respect to y and then x. The bounds in the y direction were from 1 to 2, and in the x direction from 0 to 4. So now I need to find the antiderivative with respect to y, treating the x like it's a constant, so it'll just hang out there. And the antiderivative, not too hard to find, and y is ranging from 1 to 2. Leave that minus out there, leave that x to the 1/2, and now I'll just evaluate, and that's a 1/2 minus 1. Get that -1/2, and factor that out and be a positive 1/2 now. Find an antiderivative, and now I'm going to evaluate from x is 0 to 4. You get 1/2 times 16/3 is 8/3. So we have used Fubini's theorem to evaluate this double integral using both orders of integration and get that 8/3 both times, and that's all we have to do.